So it's our pleasure today, the UQ TTA, to have a seminar from Amanda Howard from Pacific Northwest National Lab. Amanda got her PhD from Brown in 2018, and focuses on machine learning and computational fluid dynamics. And she's going to talk today about multi-fidelity methods and in training for physics-informed neural networks. And so without further ado, I will turn it over to Amanda, and we'll try to hold the questions for the end. So unless there's something, pressing clarification or something like that, then we'll ask to hold the questions to the end and then allow Amanda to present her work. So thanks so much for joining us.
Great, thank you. I can't see the chat, so if there's anything urgent, let me know.
I'll keep an eye on it.
Okay, great, thank you. So today I'm going to talk about work I've been doing at PNNL for improving training of physics-informed neural networks. And this is joint work with collaborators at PNNL and at Brown and at many other universities across the world. Let's see. Okay, so I'll start about talking about physics-informed neural networks, or PINs, and some of the issues we're trying to solve with PINs, and how we're doing that with multi-fidelity, specifically multi-fidelity depot nets, and stacking when that's not enough. So physics-informed neural networks, or PINs, for those who are not familiar, use physics instead of data to train a neural network. So this paper came out on arXiv in 2017, 2018. And has gotten tons of attention with, I think, 20,000 citations at this point. There's been tons of work done for how to improve training of PINs, but in this talk, I'll talk about what we call vanilla PINs, or the standard physics-informed neural network without all of the mechanisms that have been developed to improve training. What I'll say is we're aware of those works, and they can all be applied on top of what we're doing. So things like adaptive weighting schemes, adaptive point selection, all of those could be used on top of what we do to further improve the results. So a physics-informed neural network takes as input the variables of an ODE or a PDE and gives as output the solution to the equation. So in this case, I have kind of a generic equation here. Our inputs are t and x, and our output is s. And then we can use automatic differentiation to take derivatives of the output with respect to the inputs through the neural network. So we can build up our equation by taking derivatives of the output with respect to the input. And then our loss term that we're trying to minimize has penalty terms for the initial condition, boundary condition, and residual. So the initial condition takes a bunch of points at t equals 0, where our initial condition will be, and says, what is the mean squared error between our evaluated solution f and our exact solution u at the initial condition? Same thing for the boundary condition. We discretize the boundaries. And then for the residual term, we take a bunch of points inside the domain. How you pick those points does matter. And I'm not going to go into this in this talk, but if you wanted to improve a PIN or train a PIN, you should look into those methods. We will just pick them randomly at each iteration, which is an inexpensive, easy to implement way that actually does quite well. So here's a really simple example. This is a pendulum. So we've switched the equation of the pendulum. We've split it into two first order equations. So I have two outputs, S1 and S2. My input is time. So you can see that in my network. So I have time and S1 and S2. I'm actually going to train a bigger network, but it needs to fit on the slide, so we'll pretend it's smaller. We pick a bunch of what we call collocation points or residual points. These are the points in time where we're going to check how well we satisfy the equation at every training iteration. And then we can train our network, and we get this blue solution that's on top of the black solution. So now I have a surrogate solver for the solution of a pendulum with a given initial condition. It's 1, 1. The reason you might want to use this over a traditional solver is once trained, I can now evaluate at any time just by doing a forward propagation of the network. So it's very inexpensive compared to a traditional solver where if I wanted the solution at like 3.5, I'd have to start at 0 and work my way forward. And then if we didn't have a grid point at that point, we'd have to do interpolation. So that does increase the error a little bit. So we have the surrogate solver. It works really well. The problem is here, before I trained from 0 to 4, Now I'm going to train with my time domain from 0 to 15, and it no longer trains well. We get stuck in this fixed point. So this is a dynamical system. If you think about a pendulum, there's a fixed point at the bottom. This is 0, 0, and then there's an unstable fixed point at the top. So we get stuck at that fixed point at the bottom, 0, 0. And there's some really interesting work in this paper. This is not our work, that shows that pins get stuck in fixed points of dynamical systems. That's a local minima in the loss landscape. And so it's this really strong local minima where you can get stuck there, and then it's hard to get to the global minima, which would be the exact solution. So this is a really common problem when training pins across a wide range of problems. And it's a problem because this is a really simple equation. This is just a pendulum. So when we move to our real equations that we're interested in solving at PNNL, it's going to be even harder to train. And I'm not actually really interested in training pins. I'm interested in training operator networks. So specifically depot nets and physics-informed depot nets, deep operator networks. And the reason for that is pins map one input to one output. So one initial condition to the solution. Depot nets map the space of inputs to the space of outputs, so the space of initial conditions to the space of solutions. What that means is for a pin, if I change my initial condition, I have to retrain my whole network. For a depot net, I can evaluate the solution for a bunch of initial conditions without having to retrain my network. So they're much more powerful. You can think of a pin as replacing one forward solve of your finite element solver or your numerical solver. Depot net's going to replace that solver entirely. And once the physics-informed depot net is trained for any initial condition in your space of initial conditions and any point, xt in your domain, you can evaluate the solution quickly. But because they're more powerful, they're also more difficult to train. And training physics-informed depot nets is actually quite difficult right now in the field. So depot nets are an operator network. There are other operator networks out there. When I was doing this work, I was funded on a grant specifically for depot nets. So that's what I'll focus on in this talk. And depot nets consist of two neural networks. There's the branch network and the trunk network. The outputs of those two networks are combined in a dot product to give you your solution, F. So the input to the branch network is going to be the dependent variables. So for PDEs, that's the initial condition normally. For other equations, it can be things like measurements of the state of the system. The input to the trunk network are your space and time variables. So in the end, you get this operator in terms of the initial condition and the space and time variables. And for people who train depot nets, I don't actually train standard depot nets at any point in this talk. I'm actually training modified depot nets. The difference is we have these encoder layers that are combined with the branch and trunk network at each hidden layer of the branch and trunk. There's a paper out of Paris Parity-Karis's group that shows that this improves the training a little bit for depot nets, about an order of magnitude. So because of that, whenever we do train a depot net, we start with a modified depot net to get that little bit of extra accuracy. Okay, so when I started working on multifidelity, we had a problem on ice sheets. And what we wanted to do was uncertainty quantification of the ice sheet velocities in terms of the basal friction field. So an ice sheet is on land, and there's friction between the land and the ice on top of it, and the ice sheets are really, really big. So if you think about it, like how do you measure the friction between this giant substrate underneath and the ice sheet, given that you can't like core through the ice sheet everywhere, it varies in space, so you have to get fine measurements. There are inverse methods that can let you query that ice sheet, but they are quite friction, but they are quite expensive. So we wanted to be able to generate a bunch of basal friction fields that were approximations for the basal friction field of this ice sheet, and then propagate forward in time and see how that changes the ice sheet velocities. We do have a finite element code that takes as input a basal friction field and moves the ice sheet forward in time. 100 years, we get the ice sheet velocities, but it's really expensive to run. So this is an example of one of our simulations. This is on a 41 by 41 mesh. This is called the Halford dome ice sheet. It's a toy model. It's a dome ice sheet on a flat substrate. So we have the basal friction field beta. This is the ice sheet height, h, and then the ice sheet velocities. So we generated about 300 samples on this 41 by 41 mesh. We stuck them on our GPU. When we wanted to train a depot net to act as the surrogate for our finite element code, because then once trained, if we have a new basal friction field, instead of taking 3 minutes to run our finite element solver, we can almost instantaneously evaluate our DeepNet for this ice sheet. Problem is our data set was too large for the GPUs that we were working on. So we have 100 years of data for 300 ice sheets, 300 different basal friction fields, and it kept crashing our GPUs. So we generated a second data set. This one's on a 15 by 15 mesh. This is much less expensive to generate because it is on a much coarser mesh. It's also much less expensive to store, both in terms of the memory we need to keep this data set around for a long time, and also the memory that we need, the amount that we need to load into memory and hold while we're training our network. But it's obviously very coarse, but it does capture a lot of the key features of this ice sheet. So you can see like the velocity should be highest in the top left corner, and it is in both of these simulations. So my goal was to be able to train with both of these data sets simultaneously. And specifically, we want to use as much of the low fidelity data, this 15 by 15 data, as possible, and the smallest amount of this high resolution data. Because that's going to cut our storage costs, and it's also going to cut our computational costs to generate the data. While I was working on this and building the multi-fidelity model, my colleague was also able to improve our DeepNet codes. We were able to train with a full high fidelity data set. So we do have a single fidelity ice sheet paper that's in JCP. That's a hybrid DeepNet finite element code if anyone is interested in ice sheet modeling. But I'm going to talk about the ice sheets more for how they contributed to this multi-fidelity development. So we've made this really specific multi-fidelity setup that is specifically designed for scientific data sets. And what I mean by that is we expect the low fidelity and high fidelity data to be strongly correlated. They're representing the same physical laws, the same physical system. So it consists of 3 parts: a low fidelity subnet, and then a nonlinear and linear subnet that are going to be added together to get the high fidelity representation. So the low fidelity subnet is a surrogate model for our low fidelity data, or physics if you have physics available. And then the nonlinear and linear subnet learn the correlations between the output of our low fidelity subnet and your high fidelity data or physics. So the linear subnet learns a linear correlation. And for scientific data, we expect those data sets to be strongly correlated. So the linear correlation will be the bulk of this correlation. And then we learn a small nonlinear correction to that linear correlation. We do train a linear correlation instead of just assuming it's the identity. And the reason for that is in a lot of cases, you can have something that is pretty close to the identity, but maybe your low fidelity measurements are off by a little error. So we can correct for that with a linear correlation, or maybe you have some drift in your measurements. So they're off in one part of the domain, but closer to another part of the domain. By learning this linear correlation or a bilinear correlation, we can account for those types of measurement errors and learn more robust correlations overall. The advantage to the nonlinear subnet learning this small correction, it means that the nonlinear network can be very small and we need less high fidelity data to train it. So this is what it looks like with DeepNets. Each of these blocks can be whatever makes the most sense for your problem. So mostly I'll talk about neural networks and DeepNets today. I'll show some examples at the end using other architectures. If you have a really great surrogate model for your low fidelity data that's already really fast, instead of training a network here and introducing more error, because you will have some modeling error if you train a network on your data, you could just use your low fidelity model directly, and that will help in cases where that is a feasible thing to do. For DeepNets, we train 3 DeepNets simultaneously. So we have a low fidelity DeepNet, nonlinear and linear. Our loss function looks really complicated, but that's because we can take into account any type of data you have available. So we have low fidelity and high fidelity errors, and we can also do physics informed training. So a lot of times that means we have some low fidelity data and we correct with physics because we know the exact physics that the system satisfies. You could also have a case where you have really sparse high fidelity measurements, but a low order physics-based model that you could apply a physics informed loss to your low fidelity subnet. So that's what these terms in the loss function are doing. And then we have these 2 penalty terms. The penalty terms penalize the weights and biases of the nonlinear network and the low fidelity network. And the reason for that is we want a small nonlinear correlation. So we're going to penalize that network to make the correlation as small as possible. So we learn the maximum linear correlation. And then the low fidelity data we expect to be noisy or less accurate. So we're going to penalize the low fidelity output so that we don't overfit to low inaccurate data. So just to make this really clear, this is what it looks like with the ice sheet. The input to the low fidelity subnet is the basal friction field and height on the coarse mesh. We're going to get a coarse representation of the ice sheet velocities. That gets appended to the branch networks for the nonlinear and linear subnets. So the input to the nonlinear subnet is the basal friction field and height on the fine mesh, plus the coarse velocity predictions. The input to the nonlinear network, or to the linear network, is the velocity fields extrapolated to the fine mesh. And then the predictions of these get added together to get a prediction of the velocity field on the fine mesh. We train all of these networks simultaneously. Advantage of our methods over other multi-fidelity DeepONet methods and other multi-fidelity methods is we don't need to know the high fidelity values for the same input samples in the same locations as the low fidelity values. What that means is our high fidelity data set doesn't have to be nested inside the low fidelity data set. And that's a big advantage because you can think about cases where if you're measuring in different locations, you may not be able to get high fidelity, low fidelity data pairs for the same samples. But here, our low fidelity and high fidelity training sets can be distinct as long as they're representing the same system. We don't have to do interpolation. So some methods you have to interpolate your low fidelity data onto the high fidelity mesh. We don't have to do that. That can be taken care of through the low fidelity network. And our method's adaptable to available information. So you can use data or physics depending on your problem. So this is a really simple example, but I like it because it shows a different type of low and high fidelity data. So we refer to low fidelity data as something that is abundant but inaccurate. So for when you're doing simulations, that's often on a coarse mesh because we can run more simulations on a coarse mesh. In this case, our low fidelity data, we have a lot of points, but they're inaccurate. Our high fidelity data, we only have 5 points. And so those are going to be highly accurate. They're on my exact solution in blue. My low fidelity data is abundant, but you can see it's not very close to my high fidelity data. It is linearly correlated with my high fidelity data. So we're able to train my low and high fidelity DeepONets simultaneously. And we get 2 predictions. The low fidelity prediction is the dotted line underneath my low fidelity data, and then my high fidelity prediction is the black dashed line on top of my exact solution in blue. So in this case, if you just train a single fidelity DeepONet with those 5 data points, you get this green line, which is not able to capture the jump in the jump function. But because we added in that low fidelity data, our multi-fidelity prediction is able to capture this jump. And again, we're training an operator, not a neural network. So it's a operator in terms of A, which goes into this U, which gets fed into the functions. So A is varying from 10 to 14, and then also X. So I have the solutions here for 2 different values of A. We are able to recover the linear correlation that we learn. So the exact linear correlation is 2 times the low fidelity minus 20x plus 20, and we learn something that's really close to that. With DeepONets, you actually train a bilinear correlation, so you can see it's off by a little bit. And I like this example because it shows one of the really cool things about multi-fidelity training. So again, we're learning an operator in terms of A and X. So if you train with just the high fidelity data, we get these errors that are almost up to 20 up here, obviously not good. The multi-fidelity errors are much lower, both for the high and low fidelity data, but you can also see that those errors are strongly correlated. And they're right where the jump is. And the reason for that is our low fidelity network doesn't perfectly resolve this jump. So then the high fidelity can't. But if we were able to add more low fidelity data points right around the jump and make that jump sharper, we could then reduce the high fidelity error. So with multi-fidelity training, you can reduce your high fidelity error by adding more low fidelity samples without having to generate more high fidelity samples. And we can do more complex correlations. This is a very similar problem, but we no longer have a linear correlation, and we are able to learn the high and low fidelity simultaneously. And again, our errors are strongly correlated. So if we were able to add more low fidelity data up here for high A, we would also reduce the high fidelity error. Okay, so I'll go back to the ice sheets. This is the same problem we talked about before. And now we're going to train our single fidelity network. So just using high fidelity data with 10 and with 50 high fidelity data sets. So this is an example output from our simulations. If we train with, Okay, if we train with 10 single fidelity data sets, we get a mean squared error of 15, 16%. That's obviously too high for our predictions. We need to go to 50 high fidelity data sets to reduce that error to the order of magnitude we can use. When we do the multi-fidelity training, we have just 10 high fidelity data sets and 100 low fidelity data sets. Those are less expensive to generate, and we're able to reduce the error a little bit further. So multi-fidelity training uses 20% of the high fidelity data to get lower errors than the single fidelity on its own. And this is an example after 50 years. So the ice sheet has moved forward for 50 years. We have the high fidelity training with 50 data sets and the multi-fidelity, which is 10. And the good thing here is you can see these are very similar velocity fields and very similar errors in our pointwise errors. So the multi-fidelity training is doing as well as the single fidelity training with just 20% of the data. That was a toy model, so I also wanted to show some results of an actual glacier. This is in Greenland, the Humboldt Glacier. And I like this example because it shows a different way to think about multi-fidelity. Oftentimes when we're using numerical models, we think of coarse and fine meshes. Here we're going to fix the mesh, but use two different numerical models. So ice sheets are governed by Stokes flow. You could solve the full Stokes equations for the ice sheets, but that becomes very expensive. So instead, most simulations take approximations. So we use the monolayer higher order model as our low fidelity model, and then the shallow shelf approximation as our high fidelity. So the shallow shelf approximation assumes that the velocity is uniform through the height of the ice sheet, which is a good approximation because ice sheets are much larger than they are tall. And then the monolayer higher order model takes more approximation, so it's a lower order model. This is an example of the simulations for our glacier. And then for the same example, here's our exact solution after 100 years. If we use just our single fidelity data, we had 20 high fidelity data sets for this prediction. If you look at the magnitude of the velocities, you can see they're off significantly compared to the exact solution, but the multi-fidelity velocities are much closer in magnitude to our exact solution. And you can see that again in the pointwise errors. So multi-fidelity errors are about an order of magnitude smaller than the single fidelity errors. So again, adding that low fidelity data significantly decreases our errors without the need to generate more high fidelity data. And I said I'd also talk about physics-informed training. So we're going to apply physics-informed loss for our high fidelity now instead of using any data. So I have no high fidelity data, only physics-informed deep nets. And then our low fidelity data will be a low order on a coarse mesh and numerical solver. We're going to think about Berger's equation. And the reason I picked Berger's equation is it's a really standard benchmark for physics-informed deep nets. And the reason for that is it's a really hard problem for physics-informed deep nets. So if we do just a standard physics-informed depot net, single fidelity, at small viscosity, physics-informed depot nets fail to train well. So this is looking at the viscosity. It's decreasing from 10 to the -2, 10 to the -3 to 10 to the -4. And our error goes from about 4% to 24%. So at this smallest viscosity of physics-informed depot net, vanilla physics-informed depot nets are not able to train accurately. This is a really common problem. There's been several papers that have come out since this, looking at methods to improve it. I think the state of the art right now is it's still a 6% error, so it is a quite difficult problem for physics-informed depot nets. The thing about Berger's equation is it's really easy to write numerical solvers for Berger's equation as a field in applied math. We have, whole courses on how to do this. So we do have really good numerical solvers for this problem. So we generated 1,000 simulations. These are on a coarse mesh. And our data only errors are quite small. So they actually increase significantly when we get 10 to the -4. But even that's training pretty well with 1,000 data sets. We also considered, I call this column my worst case column. This is just 200 data sets. And so my error jumps significantly to 13%. We wanted to think about the case where maybe we don't have a great numerical solver. So we simulated that by adding noise to our data. So that's the data only with noise row. So the errors increase compared to the clean data. And especially when we don't have a lot of data, when you add that noise, the errors increase substantially. Okay, so how does the multifidelity do? So now we're going to use the data and physics simultaneously. Compared to using physics on its own, the multifidelity does much better. So adding that physics in, adding that low fidelity data in, gives the physics informed DeepONet a big hint. So it's able to do much better than using physics on its own. So for my small viscosity, we've gone from a 23% error to a 7% error. And even when we have less data, the error is significantly lower than if we used physics on its own. And the really interesting thing for me is when we have that noisy data, our physics-informed errors do not increase substantially. So this bottom row is using the data with noise plus physics. And you can see the errors from the clean data to the multifidelity with noise don't substantially increase even when we only have a little bit of data. So physics in the presence of noisy data can serve kind of as a regularizer to reduce the noise or reduce the error in our predictions. Okay, and this is an example of the output. So this is my worst case scenario. So small amount of noisy data, smallest viscosity. And our exact solution is here. The place where physics-informed DeepONets normally fail is to capture the shock that forms, or this very sharp gradient that forms at high T in the exact solution. Okay, so in this case, we trained with noisy data. So you can see our data-only prediction is kind of noisy. That makes sense. It has pretty big errors. Our physics-only solution fails to capture that sharp gradient. So that's why the solution is kind of smeared out. And again, has pretty high errors. In our multi-fidelity, we're capturing that gradient much better, and that reduces the error overall. And we can see the solution at 0, 0.5, and 1 down below. So our data only is pretty noisy, like it has these weird jumps. The physics only is smearing out the solution in here, and the multi-fidelity is doing much better than either on its own. Okay. So in that example for Berger's equation, I did have a numerical solver I could use, but a lot of the times we don't. So that's what led to the stacking networks. So here we're going to use the multi-fidelity again, but with no data at all. So we'll start by training a vanilla pin or a physics-informed DeepONet, and you get a solution. So this is for the wave equation. I'll show more plots of the wave equation later, but you can see my vanilla's pin solution here is not a great solution, but it's kind of right. It's capturing the large scale features. So we can treat this as a low fidelity prediction and feed it into a multi-fidelity network and learn a correction to it that's a slightly better correction than what we had before. But you can keep going. And so you can keep learning these corrections progressively, each time feeding it into a multi-fidelity neural network until you get the accuracy you want. I kind of think of this like bootstrapping or progressively learning a correction to a solution to improve performance. When I did this work, we actually made a change to the multi-fidelity setup. So I wanted to talk about that really quickly. Before we added the output of the linear and nonlinear networks together, we've actually changed that. And now we add them together in convex combination with this parameter alpha. That's a trainable parameter. And so we add a term to the loss function that penalizes alpha to the fourth. The reason for this is we want the linear correlation to be as large as possible, which means we need alpha to be small. Is the linear correlation is multiplied by 1 minus alpha. But if alpha is penalized too strongly, the linear correlation goes to 0, and we can't learn nonlinear correlation, so we lose accuracy. So alpha to the fourth seems to be a good balance between penalizing alpha but not too strongly for alpha less than 1. So going back to the pendulum I had before, I trained a feed-forward neural network pin 10 times. So each of the colored lines is one of those trainings. They're all initialized randomly, and so that all of the trajectories are slightly different. But you can see none of them train well. They all go to this fixed point. When we do this with the stacking, we start learning these corrections. So at each stacking step, we're getting closer and closer to the exact solution. So depending on the initialization of the network, we can follow slightly different trajectories as we get down. And we see this here. Each of these colored lines is one training, one random initialization, and we're looking at the relative L2 error as we add these stacking steps up. So we start at a relatively large error and it decreases as we go through the stacking steps and we end at a much smaller error. And they all follow slightly different trajectories, but they all reach that similar error at the end. They all do converge to the exact solution. So one case where you might really want to do this is multi-scale, multi-physics problems, where you have fine-scale oscillations. So this is a toy model. It's a sum of sines for our exact solution. And this is a case where you actually can train a physics-informed neural network for this problem quite well, but you need a really big network, even though it's such a simple solution. So if your network's too small, you get a solution that's kind of right starting at 0, but then only captures the large-scale oscillations, that's this yellow line. So that's 3 hidden layers with 32 neurons each. I need to go to 5 hidden layers with 64 neurons each to get this red line that is on top of the exact solution. If we do this with the stacking, we do learn the exact solution. And if we look at the convergence of it, my best pin result, my best single fidelity pin result is this black line. So the stacking reaches that black line pretty quickly, and then it decreases further. So we're able to get a smaller error eventually with much smaller networks. And what that means is we have fewer trainable parameters. So for a single fidelity pin with 4 hidden layers and 64 neurons, we have 12,600 trainable parameters with an error 0.65. We have to go to 5 hidden layers with 64 neurons to get 17,000 trainable parameters to get a small enough error, so 0.02. With a stacking pin, that nonlinear correlation is really small. So even though we're adding these stacking levels on, we still have many fewer trainable parameters. So 5,000 trainable parameters gets you the same error as 17,000 trainable parameters for a single fidelity pin. So we're at a 0.0249. But then you can keep going. And even out here at 10 steps, we're at 11,000 trainable parameters with a much smaller error. So basically what this is doing is moving from training one large network in parallel to small networks in serial. For pens, this does not really matter. All of these examples I can train on my laptop. It's not a significant amount of computational time in the grand scheme of machine learning. But when we get to deeper nets or we get to bigger problems, this can be the difference between training on a laptop and having to go to a GPU, using one GPU and having to find a GPU cluster. At PNNL, we're really interested in edge computing. So how do we train neural networks on tiny computers in like a wind turbine or in a drone? So this can be a method to train smaller networks in serial, but use the computational resources you have available instead of being unable to use the calculations. And this works for more complicated problems too. I like the wave equation because it shows one feature of the stacking that I think is really important. Up until this point, we've used the same equation at every stacking step. So here I have my exact solution and the stacking steps move down. So my first solution is not great, but we get a good solution when we move down to 14. And you can see that looking at the pointwise errors at the right. So an important parameter for the wave equation is the wave speed, or c. So here I have c fixed at c equals 2. What we can do instead is start with an easier problem, which is lower c equals 1, and then increase it slowly to reach our target problem at c equals 2. So here I start with c equals 1, and we slowly increase to get to c equals 2. And the reason you might want to do this is we find it gives you lower errors faster. So I have 3 cases. We have 3 schedules for how we reach c equals 2. Case 1 keeps it fixed. Case 2 and 3 start with c equals 1 and then move to c equals 2. And what we find is case 2 and 3 converge faster. Case 1 does reach a lower error eventually, but it does take longer to get there. And the reason for that is at each step, you're learning correlations between the previous step and your new step. And if your previous equation was really hard to train on, that correlation is going to be hard to learn because you're basically learning a correlation between noise and a solution. So you do better if you start with an easier problem and work your way to the harder problem. And using this lets us get to even harder problems. Like here we have c equals 4. So we're going to start at c equals 1 down here in purple, and then goes to c equals 2, and then c equals 3, and then all the way to c equals 4. And so we're able to target these problems that we weren't able to reach with pens previously. And of course, this works for depot nets as well. So you can start with a single fidelity physics informed depot net. This is the case with the small viscosity. So this was the 24% error I was talking about. And you can see my single fidelity solution in blue does not agree with my exact solution in black at all. You feed that into a multi-fidelity physics informed neural network, and you now get the orange solution that's slightly closer to my black solution than the blue. And you can keep going. So we'll do another level. I get my green solution. We're getting a lot closer, and you can keep going. So after 4 steps, I'm getting something that's pretty accurate. The best way to train physics-informed depot nets right now is using something called the neural tangent kernel. It's basically an adaptive weighting scheme. The neural tangent kernel works quite well, but it's really computationally expensive. It increases the training time for the depot nets on our GPUs by a factor of 6. But with the neural tangent kernel, you can drop the error from 24% to about 11%. So here, looking at this plot, this black line is my 24% error without the neural tangent kernel. With the neural tangent kernel, we're at 11%. The best way we found to train these physics-informed depot nets for Berger's equation is to start at the high viscosity 10 to minus 2, decrease the viscosity at each step to reach 10 to the minus 4, and use the neural tangent kernel at the same time. So that's this blue line, and we were able to go from 11% to a 6% error doing that. So we were able to improve on the state-of-the-art results for physics-informed depot nets. More work has come out since then. I'm excited to try those techniques on top of the stacking depot nets, because those adaptive weighting schemes, adaptive point selections, all can work on top of stacking. And something else that works on top of stacking is domain decomposition. So we have some work on finite basis pins that use domain decomposition simultaneously with stacking. So finite basis pins do domain decomposition through a weighted sum of using partition of unity functions. So we have 4 partition of unity functions here. We're going to train 4 neural networks simultaneously. The outputs of those neural networks get weighted by the partition of unity functions and then added together for the solution. Why you might want to use this over other domain decomposition techniques like X-pins is we don't have to worry about boundary conditions between the domains. So because we have these smooth partition of unity functions, we're not dealing with boundary conditions at each interface, and how you enforce those boundary conditions in techniques like X-pins can greatly influence your results. But we can use the FB pins on top of the stacking. So the way this works is we train 1 pin in the entire domain. We feed it into 2 multi-fidelity pins. Each has their own partition of unity function omega. So we get 2 outputs, these U's, we multiply by the partition of unity functions, and then we add them together to get our solution. And you can keep going depending on how many domains you need. So here I'll do 1, 2, 4 domains. You might want to do this for multi-scale problems or problems where you have really fine scale oscillations in one part of the domain. It makes a lot of sense to do domain decomposition in those types of problems. But even for something like the pendulum, we find that the stacking FB pins converge faster than stacking pins, and they converge to lower errors. So with the stacking FB pin, I'm able to reach a lower error than I was able to with the stacking any of my 10 stacking pins. And I can reach that same error in 2 stacking levels instead of, on here I'm over at 8. For the multi-scale problem, this makes a lot of sense. So my stacking FB pin is now converging much faster and to a much lower error than the stacking pin. And if we go back to our trainable parameters, before, to get an error of 0.006, I needed 11,000. With the stacking FB pin, I need just 8,000. So we are adding more subdomains at every stacking level, so that does increase the number of trainable parameters. But because each subdomain is only having to do a little bit of work, we can converge faster, basically. And you can also keep going. So if you say, well, I don't care about how many trainable parameters I have, I just want the lowest absolute error. Over here at 5 stacking levels, we have a lower error, but it does have 60,000 trainable parameters. Okay, so we've done some other work using multi-fidelity methods. I wanted to put the references up here for people who are interested. One is using continual learning. So in continual learning, you're constantly getting new data sets, and you want to predict the new data sets and the old data sets without revisiting your old data. What we found is that the model trained on your old data is a low fidelity approximation of the model trained on your new data. So you can use multi-fidelity methods in those cases, and it improves upon traditional continual learning techniques. And we also have a method called the conjugate kernel, which is a 0 order approximation of the neural tangent kernel. For many problems, we get very similar errors, but instead of increasing the computational cost by a factor of 6, it increases the computational cost by a factor of 2. So for training physics-informed depot nets, that can offer a huge cost savings with very similar results. But I wanted to switch base a little bit and talk about Kolmogorov-Arnold networks or cons. So one of the things I've been saying for a couple of years now is you don't have to use neural networks. You can use whatever you want in these blocks, but I never had anything else I wanted to use. Um, the Kolmogorov-Arnold networks came out in April. Um, Normal neural networks, MLPs, feed-forward neural networks use trainable weights and biases with fixed activation functions. Cons use trainable activation functions. So we use combinations of generally cubic polynomials. The input, this is just a very toy model, but we have two inputs, X and Y. We train these trainable activation functions. So you're looking at the activation functions I learned for this toy model. We add them together at the nodes. I have another hidden layer here, and then they're added together to get an approximation of my function u. Everything we've developed so far also works for cons. So we have a paper on FB cons. So here I have 4 subdomains. Each one gets its own network. They're weighted by partition of unity functions and then added together to get a solution. People ask me, when should you use a con over an MLP? And I feel like my answer changes every month because the cons paper got a ton of attention when it first came out, and there's a ton of papers that have been following it. Right now, I really like cons for noisy data. So because you're learning these splines of cubic polynomials, they seem to do really well interpolating noisy data points. So here I have very noisy data with fine scale oscillations. One of the things cons don't work well with is training large or deep networks. And that's where the FP cons come in. So here, if you're trying to learn these multi-scale oscillations, a large con is really hard to train. But with the FB cons, we can train small networks simultaneously, and we do much better. So our FB con loss becomes much lower than the con loss. And if you look at our predictions down here compared to the reference, it's hard to see, but our FBCon prediction is much better. And you can see that also looking at their errors. So our FBCon errors are much lower than the con errors. So while it's hard to train large and deep cons, you can train lots of small ones simultaneously with FBCons. And the cool thing is, as we add noise to our data, so going from 0 to 17% relative noise, our errors don't increase substantially. They do increase a little bit, but they're pretty robust to adding even quite a bit of noise. Physics-informed cons are an area that are pretty hard right now because of that same issue where it's hard to train these really large networks. So I showed, like, even for that multi-scale problem I talked about at the beginning, we needed a pretty large neural network to capture the solution. Training a large enough con for hard problems like this Helmholtz problem is quite difficult. So my reference solution, this is a normal con. This was the best I could get. Since I wrote this paper, more results have come out. I'd be happy to test those methods out. I do think they are improving the training. But when we were writing this paper, it was hard to get big enough. With the FBCon with 4 or with 16 subdomains, we can do much better. So again, instead of training one large network, we can train lots of small networks. And I'll stop after this, but I wanted to talk a little bit about multi-fidelity cons because I think this shows one of the really cool advantages of cons, and that's that they're super interpretable. So one of the things I find frustrating coming from computational fluid dynamics is when I do a traditional numerical solver, I know what each term is doing. When I train a neural network, I have no idea what the weights and biases mean. It's really hard to interpret those. But with cons, I can look at the activation functions and know what I'm learning. So for my low fidelity equation, I have 0.2 y squared plus 0.1 x cubed, and you can look at these activation functions and see, yeah, they're kind of learning, squares, cubics. My high fidelity equation is the low fidelity minus x minus y plus sine of 10x. So we restrict, instead of using cubic polynomials, we're now going to use first degree polynomials, linear correlations. So this is our linear con. It learns the low fidelity minus y minus x perfectly. That gives me my linear correlation. And then the nonlinear correlation is sine of 10x. And you can see we learned sine of 10x. And there is a slight error there. You can play with that alpha term would penalize this error if you wanted to increase it better. But you can see that we get this thing that's interpretable, and I can look at these activation functions and kind of know what each one is doing, which is really cool. One issue with cons, this is a slide I showed before for the DeepONets where we talked about the jumps, and you can see the jump was smeared out, but it was learned kind of sharply. Cons struggle to learn jumps. And the reason for that is you're fitting a cubic polynomial, like you can't fit a cubic polynomial to a jump perfectly. And so this is again multi-fidelity. So our low fidelity prediction is off because it can't capture that jump. So then that error transfers to our high fidelity prediction where also it can't capture that jump. It does much better than using the high fidelity prediction, high fidelity data on its own in red. But this is a case where I probably would use a neural network instead of a con if I had to predict something that I knew had really sharp interfaces for jumps. Okay, last example. And this is a case that I like to one of the things I care about is when should you use multi-fidelity and when does it make sense? And developing methods that make sense with real uses of multi-fidelity. So we're going to talk about flow past a cylinder. I'm going to talk about time from 0 to 200. I have a low fidelity simulation, a high fidelity simulation. So this is all my data. So I did both from 0 to 200 because this is a toy problem. But obviously we want to cut the cost of generating our high fidelity data. So we don't want to use all the high fidelity data. So a really common way to do that is to get rid of every other snapshot or, cut the data somewhat. The problem with this is I still have to run my numerical solver the entire time to get this data that's out here. It's less expensive to store and maybe less expensive to train on because you're not saving all the high fidelity data, but you're still having to generate it to get all the way out to the end. So what you want to do instead is only have high fidelity data in the beginning of your time domain, so you don't have to run all the way through. The problem with this is neural networks, cons, and MLPs struggle with extrapolation. So if you only have data from 0 to 100 for your high fidelity, it's going to be really hard to predict out to 200, which is where the multi-fidelity comes in. So when we train a multi-fidelity con, up here I have my simulation, my multi-fidelity results, single fidelity using only high fidelity. They all do pretty well up to the time 100, which we'll hit really soon. And then the single fidelity can no longer extrapolate. It can't go past 100. The multi-fidelity is able to keep going even though it does not see any high fidelity data because it has that low fidelity data to fall back on. And you can see that in the errors. So as time goes on, our high fidelity error jumps strongly at t equals 100, and then it continues to increase. Multi-fidelity error increases a little bit, but not significantly. And a question I get asked is, can you just interpolate your low fidelity data onto high fidelity mesh? If you do that, what you get is this blue error. So we are learning a correction to the low fidelity data to get to this the multi-fidelity prediction. We're not just using our low fidelity data. And that error is concentrated in the boundary layer around the cylinder, which you can see. So low fidelity simulation and high fidelity simulation, this isn't a case where we have data. So we have high fidelity data. So the single fidelity prediction does pretty well, as does the multi-fidelity. But when we reach our final time at 200, where we no longer have high fidelity data, our single fidelity solution is awful, but the multi-fidelity is able to keep going. Okay, with that, I would like to say thank you. We have coding tutorials that we've released through a PNL package called Neuromancer for scientific computing. Those are at the QR code, and you can also look up Neuromancer on GitHub. Those are focused right now on the cons and on the stacking cases. But you're welcome to play with those, and they have Google Colab notebooks that you can play with and change the parameters and see how they train. So thank you. I'm happy to take questions.
Thank you very much, Amanda. A wonderful presentation. I'd like to open the floor for questions. Susanta, I see your hand up.
Hi, great talk. Thank you. Can you share your thoughts on the time comparison for these methods compared to standard numerical method on the same system? I mean, just an approximate idea about.
Well, I think that is too big a question to answer. Certainly, training a pin is going to be more expensive in almost all cases compared to running a finite element simulation. But then what is your goal once you've trained the model? So training something like a physics-informed DeepNet will be more expensive than running a couple finite element simulations. But then you have a surrogate model for all initial conditions in your initial condition subspace. And so then you can quickly query them. So if you need 10 solutions, probably not worth it to train. If you need 1,000, that time cost may start to balance out. So it really depends, what's your goal? And what methods are you using? I do think the training times are coming down as we get access to more GPUs. And specifically for the cons, the implementations we have now are not the implementations we had 6 months ago. They are much faster. And so I would personally look at those more recent implementations if you're planning to train a con and care about time efficiency.
I see. Can I have one more small question?
Sure, yes.
So for the flow past circular cylinder, you used training data, right? So that means it's not purely physics informed. So if you use purely physics informed, can you share your thoughts on how does it perform for such problem?
So for flow past cylinders, there's some really excellent papers out there I can share with you. It suffers from the same problem that the pendulum suffered for, where there's a fixed point of the dynamical system, which is the stable solution. So the steady solution for flow past a cylinder, which is not physical, because cylinders are not perfectly smooth and round. So there's a fascinating paper that I can send you if you're interested, but basically there's diffusion that brings you back to that fixed point, even in the presence of some data. But that's kind of a special case where we know, like, people have studied this particular problem, and it is a case where pins are very difficult to train well.
Thank you.
Any further questions? Amanda, I actually have one question.
Yeah.
It's more of a practical question.
Mhm.
So these two corrector networks in the multi-fidelity, you have the linear correction and the nonlinear correction. I didn't quite pick up exactly what the inputs to those are. You mentioned that there's no interpolation required for the low fidelity onto the high fidelity mesh and those sort of things, but I didn't quite capture what goes into those correctors and how those are structured. Could you just review that again?
Yeah, so if I go back to this example, so when you're training it, you're going to use specific XY points as your training data. Like I have pairs that are, or triplets, XY, FL, XY, FH.
So I guess the question stems from your high fidelity and your low fidelity are potentially on different XY. Your low fidelity is on a different grid than your high fidelity is, and so on. Like, so how do you get those to match so that you can practically
Yeah. So this is a really important point because it brings up one of the advantages of our method. So we're going to train, I have my low fidelity set. Let's ignore composite training. So let's say I train my low fidelity model separately. I'm going to train my low fidelity model, but then I have a low fidelity model that can be queried at any set of X and Y.
Got it. Okay.
So then when I go to train my high fidelity model, I'm going to evaluate my low fidelity model at my high fidelity X and Y.
So you're using the surrogate prediction for its interpolatory capability.
Yes,
Okay.
exactly. Exactly. If you use, like, if you have a really great low order numerical solver you want to use instead, you do have to do interpolation onto your high fidelity mesh.
Okay. That answers my question. Thanks so much.
Yeah. Yeah. When you play this game, is the error from interpolation higher than the error from learning a surrogate?
Super. Thanks so much.
Welcome.
Are there any other questions? If not, we'll thank Amanda again. And again, very nice talk. This is a huge body of work. So thank you so much for sharing this with us and presenting today.
Great. Thank you.